corresponding to what your group values are, so that you use them. So this is the function for solving for doing the assignments. So this is the structure. We have two outputs, the T and C. In our case, the T is for the time output, and then the C is for the concentrations output. Because we are dealing with 4 differential equations and 4 different constants in terms of the concentration, as in C, the concentration of A, the concentration of B, the concentration of D, and then the concentration of U. So these are 4 concentrations that we are going to get as in the output from the C part of the MATLAB script. So for every group, we all have our values that we're using. So this being the structure, the time output, the concentration output, and then we are using the ode45 function. So if you are going to do it, you start by bringing the at and the name of your function. From our function down here, the name of the function is batch solver, so you can change it to anything. I'm going to change it to maybe function 1, and so I'm going to also change it here because this part should have the function name, function 1. Okay, so function 1. And then this tr here, this tr is the time that our function is going to use to integrate these 4 DEs, or to solve these 4 DEs. In this case, Sir solved only 2. He was solving only for 2 concentrations. So he solved using 3 differential equations. We are solving for 4 differential equations. So this TR is the time that you're going to use. So from the group, I'm going to use group 14. This is our TF, our time final, the time final time, TF. So it's from 0 to TF, the time final. So I'm using linspace to divide the 0 to 200 into 10. So 0 to 200, and I want only 10 divisions, TR. And then the CO is our initial conditions. Our initial conditions. So this line is where we are going to state our initial conditions. And from the group work, we have 4 initial conditions: CAO, CBO, CDO, and CUO. So I'm going to write them here. So CAO from my group is 1.05. So 1.05. CBO is 1.01. 1.01. CDO is 0, and also CUO is also 0. We are not going to be using this one, so I'm going to clear them. So now we have our initial conditions: CAO, CBO, CDO, and CUO. So I'm going to put them into one container, or in a matrix form. So CAO space, CBO space, CDO, and then we add the last one, CUO. And we are calling our initial conditions CO. So we have T output, concentration output, the function name function 1, our TR, the time that we're going to be using, that is also equal to the time output, and then our initial conditions. And now from this side, we need to know our k1 because it's in our differential equation. We have k1, k1a, k2d, k3a, the three k's, sorry. So we are going to define them. So our k1a is equal to 10 exponent 9, and also the exponential of minus 920 over t, where t is the time here. So I'm going to do that in here. So I'm not going to use this, I'll collect. First, I'll define my T, the temperature, which is equal to 550 Kelvin. So 550. And then I'll define my K1A, K2D, and K3A. So we start with K1A. K1A. So maybe you can do it KA or KA1 is equal to 10 exponent 9, 10 exponent 9 times exponential of minus 9200 over t, minus 9200 over t, where the t is our time. So that's for the KA1. So we're going to do the same thing for K2D and then K3A. So K2D is 4 exponential minus 2000 over t. K-D2 is equal to 4 times exponential minus 2000 over t. And our K3A is 30 exponential minus 3000 over t. K-A3 is equal to 30 times exponential minus 3000 over t. I am defining the Ka1, Kd2, and Ka3 in the function because if you define it outside, you have to use a certain function called the global for you to be able to use it in our calculation here. So to avoid that, I am defining it inside the function so that I don't have to do it outside. I don't have to bring the global. And now after inputting my Ka1, Kd2, Ka3, I'm now come to write my 4 differential equations. So the first differential equation is K2d times Cd minus K1a Ca Cb minus K3a Ca Cb. So we are going to write this there. And in writing your differential equations, you write it in this form. So dc1 for the first differential equation, dc2 for the second differential equation, dc3 for the third differential equation, and then dc4 for the fourth differential equation. And also you use, because for my function here I said my inputs are T and C, so I'm using C for the concentration. You can decide to use any variable, so depending on what you use here, whether C, D, E, any variable at all, you must use the same to present the concentrations in your differential equation. So because I'm using C here, let's try changing it to maybe CN, maybe for concentration. So my first differential equation is K2d so K2d. So I'm going to number my constants. I'll make CA1, CB2, CD3. Yeah, CD3. We don't have U in here, but it will be my last concentration. So CA will be CN1, CB will be CN2, and CD will be CN3. So K2D, which is this one, I don't want to type, so I'm just going to copy K2D times CD. Okay, I'm going to split my screen so that I don't have to be going in and out. So it will just be here. I just look at it and then write. Okay, so K2D CD. So times, okay, the times is there. Cn, because we are using Cn for our constant as in the concentrations. So Cn and then a bracket. CD is 3, so the third one, and then minus K1A, which is our Ka1. Going to copy and bring it here, times CACB. So our Ca is Cn1 times Cn2, and then minus K3A, which is here. Copy it, space, and then bring it, times K3A times CACB. So Ka3 times Cn1 times Cn2. So now we have our first differential equation here. The last three are almost the same thing, so I'm just going to copy and then make the changes. So I'll paste it here. This one is K2dCd, K2dCd, which is the same as the first one, minus K1A, which is this, Cn1, Cn2 for CACB, and then the third one. So the first two equations are the same. The third one will also follow the same pattern, but with the third one, the K1A CACB comes first. So this is our K1A CACB. So I'm just going to cut it. Sorry. I'm just going to cut it and then bring it in front. And it is minus, sorry, it is plus. It is plus K3A, which is this one. So I'm going to also cut it and bring it in front. So basically you just write, which is minus K2dCd, which is this one, K2dCd. So just write your your four differential equations in this format, where the constants, in our case the concentrations for each, will be C. I'm using Cn here, so Cn 1 into brackets 1 for the first one, Ca, Cn2 for Cb, Cn3 for Cd. So the last equation, which is K3A, which is this one. So I'll just copy it and bring it here. So K3A CACB. So now we have our four differential equations. Now this one, after calculating, I want to group all my results in one matrix form. So the result from the first differential equation here. In one row, the result for second, third, so in a matrix form. So space, I have 1, 2, 3. So I'm going to add the fourth one to it, copy, and then paste. So now we have solved, we are almost done with the first part. First defined my k constants. First said my t is 150, my ka1, kd2, ka3 here, and then wrote my 4 differential equations, which is the same as the one here. So let's make this one out so that it doesn't plot now. So this is our function, the OD function, initial conditions, our time, and then the initial conditions defined here. So I'm going to run the script and see the results. Okay, so I'll terminate some of them so that it doesn't show. I just want to show the final results. Okay, so running it. Okay, so there's an error. Okay, so due to the semicolon that I didn't bring here, it made an error because I want it to be in rows. First row, second, third, fourth. Sorry, I want it to be in columns. Sorry, columns. So the concentration for the first part to be first column, as you can see here. Here, the concentration for the second one here, third one here, and the fourth one. So from our results, which is the C, the output from this side, and then the time. So from 0 to 200, I divided it into 10 different times, which is here, and then my concentrations after MATLAB solve the differential equations are here. So the first part is for CA, second part for CB, third part for CD, and then the last for CU. So these are the concentrations. They are 10 because the time is also 10. So assuming I change this one to probably 1, just one time, and I run it, another error, sorry. Just say 2 different times. That's a lot. Okay, some time is a lot. Yeah, that's how it should be. Okay, so I'm going to try the 2 again. I don't know why the 2 is that much, but dividing it into 5, so 5 different times, meaning 5 different concentration for each of them. But in our case, we are doing it 10 different times, so 10 different concentrations for each of them. So now I have our concentrations. Okay, so the question said we should, on the same graph, plot the concentrations of all the compounds with time in table 1. So these concentrations here, we are going to plot all of them against this time. So we are plotting a 2D graph. So this is when I move this. So this means that the T is for the time output, which is the 0.22 point that all the way to 200, the 10 divisions that we have, and then comma. For every plot, we do it plot into bracket x comma y. Yes, but in our case, and if you are plotting maybe multiple graphs on the same sheet and you want to repeat a value, probably maybe x comma z. So that's what we are doing here. So this is the first one, this is the second, the third, and then we are going to add the fourth component. So with this same idea, we are going to have c, the time for the first part, and then the concentration. In our case, our c, is also c. This means we are taking our c values is all the values on a column. Sorry if I'm highlighting here, but all the values on this column here. All the values on this column here. So this is row, this is column. So column 1, all the values on that column. Column 2, all the values on that column. Column 3, all the values on that column. So we add the last one to it. So t comma c into bracket our column comma and then 4, showing the fourth column. So we are plotting t against all the concentrations in the first column, t against all the concentrations in the second column, which is the concentrations of B. The first column is the concentrations of A, second concentrations of B, third concentrations of D, and the fourth one is the concentrations of U. So T concentrations of D, which is the third column, and D concentrations of U, which is the fourth column. So if I plot, the graph will come. So these are the concentrations of my concentrations, my graph A, my assignment, for group 14. So this is the graph. First of all, you define your T. You also write expressions for your K values, KA1, KD2, KA3, and then you write your differential equations here in this format. First differential equation, dc1 for first differential equation, dc2 for second differential equation, dc3 third differential equation, dc4 for the fourth one, and then you write them. So from our differential equations, we have k to d, which is k to d, cd, and cd, from what value you use here, the variable you use here, that's what you're going to write. So if I'm using cn here, you can use c, you can use a, but anything you use. So a into brackets 3 for the third one, that is the d. So I can also change this one to 1, which will make my first column the concentrations of d. But for me not to be confused, I did it in that order: a, b, d, u. So 1, 2, 3, 4. So you can choose to do it anyhow, just that make sure it doesn't confuse you. So that's how you do it, and then you get your concentrations. So if you want to terminate and you don't see this output here, you can just terminate here, and then the batch, it will just run here. But if you want to see your results, you remove it and then you run. Good. Okay, so the other aspects. So we successfully plot all this on the same graph sheet. Now the B says plot the concentration profile of compound D at 5 different temperatures. You can choose to do it here, but for me I thought it would confuse me, so I decided to do it on a different script. It follows the same procedure, just that for this part your T is changing, and as your T is changing, your K values will also change, and if your K values change, your concentration output will also change. So if you can figure a way to do it at the same time, it is good. But because I couldn't find a way to do it at the same time, so I decided to do it one by one, and this is how I did mine. I wrote an expression for the time. So probably t is equal to the interval that was given. So for my group 14, our time range was 500 to 570. So 500 comma 570 comma 5 different divisions. And so I come here, sorry, let's put it in a function, otherwise it might confuse. So paste. So this code divides the temperature range into 5, and then I wrote 5 different functions for each by calling the first one. So if I copy this and I bring it here, and then I run the script, I'm going to see my t, which is 500, 517, 535, 552.5, and 570. So for the first one, my t is going to be the t that I divided, which is this line, and I'm going to call the first component 1, and then use it. Then you write a second code for the same thing. So I'm just going to copy and paste. This one is going to be 2, so I'm using the second t of this. So if I remove this and also remove this, but terminate this and then terminate this, I just want to see the values. So, and also terminate this. There's an error somewhere. So we have, okay, yes, I'm having 2 different functions here, but my function for calculating the differential equation is 1, and also the names are the same. So that's why I started by saying function 1 here. You can do it anyhow. So I'm going to change this to function 2, and then I'm going to copy this differential equation and then change this here to function 2. Now I have 2 different ones. So when I run, it calculates. This is it, but that's not what you want. So my t, as you can see, sorry, it's a lot. That one I don't know why, but okay. So the first one use the first, and the second one will use the second one. So that's how you do for the second assignment. You write different functions, and then for every function use a separate time. Use the first time for your first function, second time for the second function, third time, and so on. That is for the, and after that, the results. So if I run, let me just terminate this. Let me terminate the function so that I see the results. So I have 2 C's. So let me terminate this and also this. So I have 2 C's. This is the function. So the first T, that's the time for the first function and its concentrations, and then the second time and its concentration. So I have a C here and another C here, and from these 2 C's, the first column is the concentrations of A, concentrations of B, concentrations of C, and concentrations of U. Same here, CA, CB, CD, and CU. So we are plotting the graphs of just the CD. So you take CD here and take CD here. How are you going to do it? So when you come to your plot, instead of, and also change these values, otherwise they are going to be the same. So if the first one is TC, the second one will probably be let's just use any variable P K. So I'm going to plot the first part T against, this is the third column, so I'm going to change this one to column 3 of this one, and then now this one, the concentration is now K of also column 3. So you do it for all the 5. I've just done only 2 here, so this is it. So when I run, it's going to plot the concentrations of only 2, but in your case 5, because you're going to do it for 5 different ones. So this is the D concentration, the first one in the blue, and the second one this for the concentration. So you did for all the 5 different ones. And the third part says, on the same graph, plot the graph of yield and selectivity of compound D with respect to with time. So this is the formula for finding the yield, which is the concentration of D. So you do it again. So from this example, there's our concentrations. So I'm going to write a function like yield is equal to yield is equal to concentration of D, which I know from the first part it is C, all the columns of all the third column, comma 3, divided by concentrations of the initial concentration of A, which is CaO. So this calculates my yield. I'll do the same thing for the selectivity here, CD over Cu plus E. This can be any number, but it should be very, very small. So if you look at our concentrations, the least number is probably 0.08 here, but maybe for the other ones it will decrease. So maybe 0.000001 could be my this, and then you calculate for selectivity. And also you plot a graph of the yield and selectivity of compound D on the same graph. The same thing you do for the D, you plot a surface graph, and then you are done. I hope this video is helpful. It's a lot, but I hope it helps. Okay, so that is it. If you don't get anything, you can ask me, but I hope you get it. Okay, so bye. Okay, bye.